Okay, so we have covered the first 6 topics in first 6 sections in topic 1, right? So next, let's have a look at exponential and logarithmic functions. So before we look at these functions, first let's have a look at some laws of exponents and laws of logarithms first. So on the left side, these are some laws of exponents. Make sure you are familiar with all of these. First of all, if the base numbers are the same, a to the power of m times a to the power of n can be written as a to the power of m plus n, right? And a to the power of 0 is always 1, where the base number is not 0. And the quotient between a to the power of m over a to the power of n can be written as a to the power of m minus n. And a to the power of negative n equals 1 over a to the power of n. And similarly, 1 over a to the power of negative n is actually a to the power of n, right? And have a look at other laws. Make sure you know all of them. And similarly, for laws of logarithms, we have, if you have a same base number, the logarithm based on a of xy can be written as log base a of x plus log base a of y, right? Of course, you need to ensure x is greater than 0 and y is also greater than 0. And also have a look at of the other laws by yourself. Make sure you are familiar with them. Okay? Any questions? Alright, and next, if you have a to the power of x equals a to the power of k, that means x equals k. And also note that we can rewrite the exponential expression to a logarithmic expression. They are actually interchangeable, right? For example, a to the power of x equals b is equivalent to, say, x equals log base a of b, right? Did you get it? And based on this, we have x equals log base a of a to the power of x, and x equals a to the power of log base a of x, provided x is greater than 0. And the natural logarithm is the logarithm in base e. For example, if you have log base e of x, usually we can write this like line x. And another commonly used logarithm is log base 10. Log base 10 of x can be written in log base 10 of x like this. You can just skip the base number if the base number is 10, right? And last, we have the change of base formula. If you have log base a of x, then that can be rewritten as log base b of x over log base b of a. You can change the base from a to b. Okay, again, I'm not gonna prove each of the laws for you. You can try this by yourself after this class, and if you have any questions, just let me know, okay? Okay, next let's have a look at an example. Can you simplify and state any restrictions on the variables m using what we have learned so far? Okay, let's have a look at the solution together. So according to the law of logarithms, we know the base number are both 10, right? So log base 10 of the first expression subtracted by log base 10 of the second expression can be written as log base 10 of the quotient of the two expressions, right? And then factorize the number here, which is 2 times x m plus 3 times m plus 3 times m minus 3, right? So first of all, the restrictions. So if you have a number as an input of logarithm, you need to ensure m plus 3 cannot be 0, and m minus 3 cannot be 0, which means m cannot be, oh sorry, made a mistake here. The restrictions means this is the input of logarithms. This is another logarithm of input of logarithm, right? So you need to ensure 2m plus 6 must be greater than 0, and m squared minus 9 must be greater than 0, right? So this is equivalent to, first of all, m is greater than negative 3, and m is greater than 3, or m is less than negative 3, right? So we need to find the overlapped area between these two expressions. So you can simply draw a number axis to find the common part. The first solution is x must be greater than negative 3. Second solution is m must be greater than 3, or m is smaller than negative 3. So the only overlapped area is here, which is m must be greater than 3. So this is the restrictions on the input m, right? So if you ensure m is greater than 3, this can be written as log base 10 of, we can safely cancel m plus 3 here. Because m is greater than 3, so m plus 3 cannot be 0. So that's log base 10 of 2 over m minus 3, and the domain is m is greater than 3. Did you get it? Okay, so let's have a look at another example. Suppose you have a function, equation like this. Are you able to solve the value of x that makes this equation be true? Any thoughts? Okay, so note that we have something in terms of 4 to the power of x, right? Then we could use substitution method. So we could let, for example, 4x equals a variable u. Then the original expression or original equation is equivalent to u to the power of x, u to the power of 2, right? Minus u minus 20 equals 0. So that transforms the original equation to an equation you are familiar with, right? This is a quadratic equation which we can easily solve. As long as you can solve u, you can solve 4 to the power of x, right? So this can be factorized to u minus 5 times u plus 4 equals 0, right? And therefore we have two solutions, either u equals 5 or u is negative 4. The problem is, can we accept both of them? So note that u equals 4 to the power of x. No matter what x is, 4 to the power of x is always positive, right? So here u must be a positive number. So you cannot accept anything other than a number from 0 to positive infinity. So we can accept the first number here. U is 5 has no problem because 5 is greater than 0. But u equals negative 4. This is not possible, right? U cannot be a negative number. So you need to reject this solution. And therefore, if u equals 5, we have 4 to the power of x equals 5. And that means, remember, we can rewrite this to logarithmic expression, right? That means x equals log base 4 of 5. So that's your solution. X equals log base 4 of 5, right? Alright, next let's have a look at the properties and graphs of exponential functions, and then followed by logarithmic functions. So for exponential functions, you could have two different types of graphs depending on the base number b. Suppose we have an exponential function of this form, y equals b to the power of x. Of course, the base number b must be greater than 0 and not 1, right? This is the definition of exponential function. Did you get it? And the graph looks like either this or this, depending on whether b is greater than 0, b is greater than 1, or b is greater than 0 or less than 1. Did you get it? If b is greater than 1, we have an increasing function like this. The domain is the whole real number set. The range is 0 to positive infinity. The y-intercept is 0, 1, and it has a horizontal asymptote at y equals 0. The function is increasing on its domain when b is greater than 1. Otherwise, if b is greater than 0 and less than 1, you will have a decreasing function in the whole domain. Domain is also the real number set. Range is 0 to positive infinity. Y-intercept is 1, and the horizontal asymptote is the line y equals 0. You see that? Alright, then let's have a look at the graph of logarithmic function together with its properties. So note that if you have a exponential function, we can solve x in terms of y, right? Then you will end up like a logarithmic function. So if y equals b to the power of x, we can easily solve x is actually log base b of y, right? And then interchange the position of x and y, because usually we'll use x as input and use y as output. So this function here is the inverse of this function here. Note that when we learn general concepts in functions, a function with its inverse is symmetrical in the line y equals x, right? So the graph of logarithmic function will be symmetrical with the corresponding exponential function in the line y equals x. So this line is log base b of x for b is greater than 1. And in the second case, this is a graph of y equals log base b of x for the case where b is greater than 0 and less than 1, right? Can you see that? Okay, let's have a look at the main properties of logarithmic functions. So according to our analysis, you can easily see the blue curve in the two graphs here are the graphs of logarithmic functions with b is greater than 1 or b is between 0 and 1, right? In the first case, you will have an increasing function. And when b is between 0 and 1, you will have a decreasing function. In both cases, the domain of the functions, logarithmic function, is from 0 to positive infinity, open interval. The range of that function is a whole real number set. The logarithmic function has vertical asymptote at x equals 0, right? Did you get it? And the red curve and blue curve are symmetrical in the line y equals x because they are the inverse of each other. Okay, any questions? Okay, if you don't have any questions, let's make a summary for exponential and logarithmic functions. So first of all, the simplest exponential function is fx equals a to the power of x, where a is greater than 0 and a is not 1, right? If a is greater than 1, we have a growth function or increasing function. If a is less than 1 but greater than 0, we have a decay function or decreasing function. The graph of y equals a to the power of x has the horizontal asymptote y equals 0, right? Again, we can also expand this idea a little bit. The general exponential function can be expressed as a to the power of x minus h plus k. So here you have two parameters that control the transformation, right? A controls how steep or how steeply the graph increases or decreases. H controls horizontal translation. K controls vertical translation. The equation of the horizontal asymptote is y equals k, right? And the logarithmic function y equals log base a of x, where x is greater than 0, is the inverse function of y equals a to the power of x. The graph of it has the vertical asymptote x equals 0. the natural logarithm function y equals ln x, x is greater than 0, is the inverse function of y equals e to the power of x. Okay? Alright, so let's use what we have learned to solve some example problems. So first of all, suppose we have a inequality like this. Can you solve this inequality? 2 to the power of 3x is greater than 4 to the power of x plus 1. You can use a property of exponential function or logarithmic function to solve it, right? Okay, let's have a look at the solution. Usually, if you see exponential inequality, we can change the base to the same number, right? So original expression is equivalent to 2 to the power of 3x is greater than 2 to the power of 2, then to the power of x plus 1, because 4 equals 2 to the power of 2, right? And this is equivalent to 2 to the power of 3x greater than 2 to the power of 2x plus 1, right? Then you can consider this function. Consider the function y equals 2 to the power of u. This is actually a increasing function whose graph looks like this, right? It's an increasing function. So when the input is larger, you will have a larger output, right? So the left side is the image of that function. The right side is also another image of that function. So in order to have the left side is greater than the right side, we need to ensure 3x is larger than 2x plus 1, right? Because larger input means larger output, right? So as long as you ensure 3x is greater than 2x plus 1, you can ensure 2 to the power of 3x is greater than 2 to the power of 2x plus 1, and vice versa. It's actually equivalent. And this is equivalent to x is, oh sorry, we have a 2 here. There's a typo, sorry. So that means x must be larger than 2, right? And of course, you can also consider it like this. From here, you can find log base 2 of both sides, right? Log base 2 is an increasing function like this, right? So if the left side is greater than the right side, that is equivalent to log base 2 of the left side must be larger than log base 2 of the right side. And according to the power rule, the left side equals 3x times log base 2 of 2, which is 1, right? Is larger than 2x plus 2 times log base 2 of 2, which is also 1. So in this way, you can also solve x, which is x must be larger than 2, right? Did you get it? Alright, if you don't have any questions, let's consider another sample problem. Here. Can you graph the function y equals negative log base 10 of x minus 5, then plus 2? Well, usually if you graph a function, you should label its x and y intercept, if any, and x and y asymptote, if any, together with some key point. If there is any, right? So how do you sketch the graph of this function here? We need to refer to the function transformation theory, right? Because we know the graph of the base function, y equals log base 10 of x. Okay, I'll give you some time to consider this, and after that, we'll have a look at the solution together. Alright, let's have a look at the solution. So, first of all, let's consider the base function, y equals log base 10 of x. Note that there is a connection between the target function and the base function, right? In the target function, note that we can locate the 4 parameters that we can use for the transformations. First parameter is a, which is -1, right? And then k equals 1, so we don't care about k, and d equals 5, right? And c equals 2. So based on the original function y equals base 10 of x, we can do the transformation corresponding to a first. So the base function looks like this: log base 10 of x. It will cross a point 1, 0 here, right? So first of all, we need to reflect this function in the x-axis because we have a equals -1 here, right? After the reflection, the function looks like this. Also cross a point 1, 0. And after that, we have a parameter d, which corresponds to a horizontal translation to the right by 5 units, right? And then after the transformation corresponding to d, the function moves somewhere here. And also the vertical asymptote also moves, also translated to the right by 5 units. So this line here is at x equals 5. And this point here becomes 6, 0, right? And we have a last transformation need to carry out, which is vertical translate up to 2 units by 2 units, right? So after the last transformation, the function still have this shape, but the anchor point 6, 0 becomes 6, 2. Okay, so the shape of this function is here. And this point is also 5. And actually you can calculate this point. If you let y equal 0, then we have log base 10 of x minus 5 must equal 2, right? That means x equals x minus 5 equals 10 to the power of 2, and x equals 105. So this point becomes 105 here, right? And actually you can also mark another anchor point here, because we already know when x equals 6, this part is 0, and the whole expression becomes 2. So it must across another point 6, 2, right? So these are the all key points on that function. So you could use this graph as a sketch of the function, a sketch of the graph of this function, right? Did you get it? Okay, so if you know the graph of this function, basically you know everything, right? Of course, to this particular question, without the graph, you could also analyze this domain, range, and equation of asymptote, right? So according to the graph, or according to the expression itself, we know the domain, I'll just write it here. The domain is from 5 to positive infinity, open interval, right? And the range of that function is the whole real number set, or from negative infinity to positive infinity. The vertical asymptote is the line x equals 5. Did you get it? Okay, so that's the end of exponential and logarithmic function. And next time we'll talk about trigonometric function. We'll leave this to our next class, okay?